So today I'm going to talk about isolation, digital design development, and we are going to use mefenamic acid as the magic case study is 1.5 years we are trying to address. And I'm going to use mechanistic modeling. So this should be how usually people are doing manufacturing of an API. So you have synthesis, purification, crystallization. In this case, for mefenamic acid, the original idea was to do 2 times crystallization filtration. So where in crystallization and isolation 1, the goal was to maximize the purity because we had impurities, several related impurities of mefenamic acid. While then we had also a second crystallization and isolation stage that was used to define the particle size and shape. So what I've done in the last year or so, I've developed isolation models, so filtration, washing, deliquoring. I'm currently also addressing the gap of convective drying. And the idea is to digitally predict and design optimal isolation for this mefenamic acid. And the idea is why? Because we want to go do some in silico analysis, decide with that, okay, what are the optimal conditions to do my process, and then go in the lab, save time, save solvent, material API, and make the process a little bit greener, and being able to isolate mefenamic acid. So you have seen in the last presentation a slightly different version of the digital twin and microfactory workflow. So this is, how can I say, a really simplified version. Really simple. So basically here you have the different stages that you should follow to do collect some preliminary experiment, design the best experiment to conduct, then go prepare your model, design your model, do parameter estimation. With the parameter estimation, you are going also to do validation of your model, so you're sure that your model is not giving you random results. And with the validated model, what you're going to do, you are going to do uncertainty analysis. So the idea is if your factor input parameter of your process are in a range, and you want to see how the variability of your process are affecting the results of your analysis, you do an uncertainty analysis. With the uncertainty analysis, then you do a sensitivity analysis that is giving you, okay, if your input parameters are changing, okay, use these that are the optimal parameter. And then finally, you go in the lab and you start with your big equipment to do experiment. So the model I've developed is here, is structured here. So I've done a filtration model, so using a batch pressure filter. All of these models were generated using GPRON's formulated product, and basically what we have. Filtration model using Darcy law. Everybody knows Darcy law, so I don't need to explain it. What we have used Karma-Kozeny equation to basically get the cake resistance estimated from the model, and we have decided to do filtration stop to dry land because what we are using then an equipment in the lab that is the AWL unit CFD25 to filter our product, and that equipment is stopping filtration to dry land. So this means that you have your filter cake after filtration that is saturated with liquid. Then, washing model. Washing model you have that you use the output from the filtration model, and you basically use a diffusion dispersion mechanism approach that is the best one to basically simulate the shape of a washing curve. And in this case, we have decided to don't include the dissolution or growth mechanism. However, I'm working already on the development of a washing model that is also considering dissolution, because that is a really important mechanism, especially when you are working with organic compounds that can easily dissolve in your crystallization and wash solvent mixture. So then we have also the deliquering model that is a custom model. So, and what you can get from this model is the saturation of the cake based on the driving force you are applying. So here is the modeling approach I've used. So first, what you want is input parameter from the upstream process. So in this case, what I needed the crystallization model results that Dr. Wei Li is going to present later on. After that, what I've done, I've used those outcomes as feed information for my isolation model. And to do the parameter estimation and validation, I needed to do few batch experiment in the lab to validate the model develop. So I've used some filtration, washing, and drying batch experiment that a master student I've co-supervised was collecting. Then filtration. Then what I've done, I've used the validated model to basically take the experiment done in a continuous run to revalidate again the model, because one time is not enough. And finally, getting the parameter that Dr. Wei Li was obtaining from her continuous crystallization model, I was basically then tweaking my isolation model to be able to get reliable results. So, as I said, I've used a different set of equipment to do my batch and continuous experiment. As you can see on the left side, you have batch filtration, washing, and deliquering tools. So this is a simple biotage equipment that is using biotage filter with 20 micron pore size, and the medium resistance is a plastic medium resistance. Then I've developed with one of the master students I was co-supervising this convective drying manual unit. It's quite simple, but it's able to get what I needed. And then these were used to first validate the model. Then what I've done, I have revalidated the model using instead the AWL CFD25, that is a continuous isolation platform that is capable to do both batch in optimization mode and continuous isolation. So these are the two sets of suspension that I got from the campaign we have done in November 21. So we were generating two different kinds of particle size, and these that you see on top are the schematic view of the model that Dr. Wei Li was developing. So, the slurry generated, the value that you have on the bottom are the values that were experimentally generated. So you can see that we had different particle size and size distribution, and slightly different solid load after crystallization. So what I've done, I've used those data for validating my model the second time. So what you can see here, so I was initially feeding the model with the initial parameter that you see on top. So these are parameters that I was getting from the batch experiment that the master student did. So then, using these parameters that are coming from mefenamic acid case study with same solvent and so on, but different particle size distribution, as you can see from the image, I've used this data and the results of the continuous run to be able to perform a parameter estimation and determine what kind of filtration parameter I'm going to get if instead the filtration flow rate and so on are given from a slightly different suspension with slightly different particle size and distribution. So just to make sure that the parameter estimation and validation was making sense, I've done also an analysis to estimate the goodness of the fit and the goodness of the model. And what you see here is that the model is capable to predict basically the experimental outcome of the continuous run. And then, since I was validating the model, the filtration model, since, as I said, the filtration output are input in the wash model, I didn't need to then validate also the washing model because the filtration model was already validated. So here what you can see is the results of in the top table, you have the results of the validated filtration model, and you can see, you can compare the simulated and the experimental results. They are comparable. And then what you can see in the bottom part of the slide, you have instead the simulated washing process. What you can see is that from the washing simulation, you can see that basically we are able to remove the impurity that in this case are the crystallization solvent and the residual mefenamic acid in solution in the crystallization solvent using just 2 washes. This is quite convenient because in this way what we can do, we can use then the AWL unit in continuous mode with one of the port that is dedicated for the liquoring, and in this way what we can do, we can then facilitate the drying process because with the liquoring we are able to remove already part of the solvent, and we are starting drying already below the critical residual solvent content, so we are minimizing risk of agglomeration. So, and here you have the comparison of residual 2-butanol after wash 2 and after drying. The after wash 2 are simulated value, while instead the results you can see here after drying are results obtained from the experiment, the continuous run done in November, and we have used the SIFT-MS in as offline technique to basically monitor the head space of our dried sample. So then here you have the liquoring simulation results. As I said, since filtration was validated, washing didn't need validation, and the liquoring model didn't need validation as well. So here what you can see, I've done a series of simulations to try to understand what is the optimal delivery time and delivery pressure to be able to reach that residual solvent content that is able to facilitate our drying. So then we are able, with a drying process, to meet the residual solvent content that is required for the specific solvent we are using. So because we cannot leave tons and tons of residual solvent in our compound, especially because we are talking not about water, but we are talking about toxic solvent, and we don't want then that our patients are eating it and dying. So then here you have some of the uncertainty analysis I've done with the liquoring model, and it was quite nice to see that usually for filtration and washing, parameters like surface tension are not really used, because those are parameters that are more related to contact angle, wettability, and so on. But instead, for the deliquoring process, you can see that the surface tension of your residual solvent is making a big difference in what is the final saturation of your cake. So this means that one of the points we should get is to basically start also analyzing parameters that are not so commonly used. So, okay, to summarize, the idea is this project was done because pharmaceutical manufacturing is moving to continuous processing. And, well, here, especially here in Glasgow, last year we had COP26. So it seems that environmental impact, these kind of things are kind of important. So why not moving also pharmaceutical industry to have a better input footprint on the planet, no? So the idea is how to do that. The point is use digital design to predict your process, and then you are just using much less solvent, much less waste. You're producing much less waste to then be able to do what you were used to do in the past. And here what I wanted to do is an example on how to use mechanistic models to be able to predict processes and then go in the lab and do it just with one or two experiments. So there are lots of people, as you can see, that I would like to thank. There is also the funding body that gave me the money to do this work. Also, I was part of this leadership program for women, and they kindly gave me money to being able to learn how to use GPROMs, because before 2019, GPROMs was like, oh, no, that is too difficult for me. But now I'm able to use it, and I use it also in an efficient way. And if you have any question, please ask.
So I'm going to talk about model-driven crystallization design and development for mefenamic acid. So the purpose of this work is to develop a mechanistic kinetic model from batch crystallization to perform a robust, optimized digital design of a continuous crystallization. So to achieve this objective, I went through the following steps, which I'll go through sequentially in the course of this presentation. So firstly, it's a parameter estimation via different size mechanisms, and then followed by the parameter validation through batch dynamic nucleation control experiment. and then access the uncertainty and the sensitivity analysis to explore the design space of continuous crystallization, and finally, the comparison between experimental and simulation results for the continuous crystallization 5-stage MSMPR. So the background of this work involves the development of a microfactory process, building a digital twin for end-to-end drug manufacturing process, from the API molecules to the final drug product performance. So as mentioned in Sara's presentation, it's crucial to see the CQAs of crystallization effects to the subsequent isolation steps, like filtration, washing, and drying steps. And also from yesterday's talk, allow us to understand the metadata standardization to achieve the knowledge interoperable and also the data usable. Also today's Marie's talk. And also we learned how to achieve the robust control using big data with AI with Brahim's talk yesterday. So in this work, we aim at to use the minimum set of a well-designed experiment to build a first principle population balance model. Especially for the experimental data is not sufficient for the APIs. So, so a workflow is demonstrated to study MFA as a model compound. So the workflow is to start from the batch data collection with finding the optimum fitting parameters, and then follows on the uncertainty and analysis and uncertainty and sensitivity analysis. And then we perform some model optimization through the continuous crystallization. And finally, we perform the validation of a continuous run to compare with the experimental results. So the first step of the digital crystallization is to design experiments and identify the mechanisms. So the image and the drawing here shows that the batch crystallization setup with the corresponding PAT tools fitted for the data collection. And so for the right-hand side, the flow diagram can see is the stepwise seeded cooling and heating experiments to assess the growth and dissolution kinetics. And also the seeded and unseeded cooling crystallization used to estimate the secondary and primary nucleation. And finally, we use a seed from wet milling experiment, which can generate a higher surface area to access the agglomeration parameters. So all the estimated parameters are highlighted in the red here. So different mechanistic models are evaluated at the preliminary stage. So for example, the events kinetics for the secondary nucleation kinetics, which subjected to the alternation between the crystal and the impeller impact was selected over power law kinetics, as it has a slightly better fit. So the upper part of this slide shows the parameter estimation results for the dissolution experiment. You can see the fitted concentration and the particle size shown in the red color with the fitted experimental data in the blue dots with the error range. So it shows agrees well with the parameter estimation results. So the bottom part of this slide shows the model was validated using the more complex dynamic nucleation control experiment with temperature cycling experiment. So the predicted concentration and the medium size D50 will agree well with the experimental data, but we can see a slight deviation for the D10 and D50 quantile particle size. So the estimated parameters with a 95% of confidence interval shown in this table. And the quality of the parameters estimated were described by the confidence domain, and we can access the parameter precision and also the degree of parameter correlation presented on the right-hand side of the confidence domain plot. So the example here on the right-hand side shows the growth and as well as the saccharine nucleation parameters are strongly correlated. But we can see at the bottom with the highlighted in green graph, it shows like it's a large confidence interval, especially for the saccharine nucleation kinetics. And the parameter uncertainties can be further reduced using the optimal design of experiment. So this work is currently ongoing. So these parameters with their 95% confidence domain intervals were used for later parameter uncertainty effects on the continuous crystallization process. So following on this, after the parameter estimation, the optimization studies is carried out for a 5-stage MSMPR crystallization using the same kinetics parameters presented in the last slides to achieve the maximum particle mean size. So the constraints, including the optimized 5-stage temperatures. So the temperature was selected within the lower bound from the operational perspective at most suitable temperature for the later stage of filtration and washing at 20 degrees. And the upper bound, the 60 degrees, was selected for considering the minimum degradation of the solvent evaporation. And also the seed was generated from external milling device. The flow rate at 10 gram per minute was determined by upstream unit operation. The total volume of the MSMPR crystallization is 1 liter with the same distributing volume at each stage. And this was ensured using the existing equipment in the CMAC lab. And this graph shows the currently setting for 5-stage MSMPR crystallization setup in the lab. You can see on the bottom left figure, the best optimal temperature is a spatial temperature cyclic across in each stage is allowed the growth and the dissolution occurred in the same at the same time in one continuous run. And the spatial temperature cycling with the alternative growth and the dissolution leading to a small population density of large crystals. And you can see the particle size, final particle size at the top here from the seed to the final particle size is shifted to the larger particle size. And also the population of the crystals significantly reduced comparing the first stage to the last stage. So this optimum spatial temperature cycling is kind of mimicking the temperature cycling in the batch system. So the operating point at the steady state is showing the temperature cycling strategy can be understood by the solubility diagram. And apparently stage 2 and stage 4, which have a higher temperature design, is apparently crossing the solubility line. So that's the dissolution occurred at the stage 2 and the stage 4. So it's allowed the dissolution of the fines at the stage at the higher temperature. And the stage 1 and 3, 5 is mainly for the crystal growth. And finally, the results are compared between with and without the Gaussian model for this maximized size case. with the offline measurement from the mass sizer. So the offline measurement from mass sizer of the final product particle size is highlighted in blue. And the bracket, the particle size, which in the bracket is the sonicated particles. So there is a two method we're using to measure the final particle size using mass sizer with and without sonication. So the objective to measure the particle size and with and without sonication is to describe, we try to describe the individual and agglomerated particles. We try to use the sonication to break the agglomeration and then measure the particle, try to measure the particle size, individual particle size. And we can see the sonicated particle size was shown in the brackets with the simulated particle size is quite much closer to the unsonicated particle size. But with the agglomeration model incorporated, the particles, the simulated agglomerated particles is much bigger than the offline measurement. So clearly, this is need further validation, and we're currently running another continuous run soon in the CMAC lab, and further twisting the model to get a better fit for the continuous crystallization. And some global sensitivity analysis were done through the confidence interval of the parameters estimated. So this is a 5-stage continuous run. So for each of the stage, we contained a lot of parameters. So this one shows the example of only growth parameters with their corresponding confidence interval effect on the final critical quality attributes. So the most influential model parameters highlighted in the yellow color here, it shows like the growth supersaturation order at the 5-stage has the most influential impact on the yield and the smaller particle size. But for the growth supersaturation order at the 4th stage, have more exhibit higher impact on the D50 and D90. And further, the effect of the growth parameters uncertainty with their corresponding intervals on the confidence band of the critical quality attributes for the concentration D10 and D50, D90 were shown in this graph. So the red circle is the offline measurement from the continuous crystallization. So we can see here the experimental measured data, which in the red circle here, with every 3 residence time, falls in the confidence domain of the concentration D50 and D90, but a slightly deviation for the D10 in this case. And similarly, we run the operating parameters for the temperature across each stage and also the flow rates. And we can see the sensitivity of the yield and also the quantile particle size changing with a different temperature and the flow rates. So we can see like the critical quality attributes of the yield and the particle size are more sensitive to the flow rate, and especially the flow rate at the 3rd and the 4th stage. And we plotted the 2 most important factors, the flow rate at the 3rd and the 4th stage, on the yield and the medium size, which shows the contour image on the left-hand side. We can see the top graph shows like the lower flow rate at the 3rd stage, and the higher flow rate at the 4th stage result in a higher yield. And the bottom here shows like the larger medium particle size mainly result from the 3rd stage flow rate. So both of the lower flow rate can lead to higher yield and the larger particle size. So it allows us to identify the design space to maintain the consistent product quality. So here comes, to sum up this work, so the digital crystallization workflow is developed. with parameter estimation and uncertainty and sensitivity analysis. So further, after look of this work is we will run the microfactory validation run with a continuous crystallization. And the further validation will, is currently ongoing. And also we working on the optimal design experiment to reduce the parameter uncertainty. And I would like to acknowledge the Loughborough group and also the huge thanks to the people from the Strathclyde, and they helped me to generate the continuous crystallization experimental data. And thank you for listening. Happy to
This presentation probably should be given by Srai and Paminda and other colleagues, so my thanks to them. But I think Lorna and Alistair asked me to do it just to ensure my attendance. I wouldn't have missed this event for anything, but anyway, thanks to my colleagues at the start, and I'll walk you through our work. I'm going to talk around three topics. One really around from molecule and technology selection to supply network design, and the workflows we've used in trying to understand the supply chain, which is a little bit different from some of the fantastic work we've just heard from the three ladies, which I'm feeling very intimidated by at the moment. The second area, which is a question the Cambridge team is regularly asked, is what's the business case for a microfactory? And I just wanted to share some of the thinking we've done in this space, where we've got a way of looking at the problem and the opportunity, of course, and where we're going next in terms of whether facilities need to be distributed closer to where the demand is, or perhaps co-located to get economies of scale at a site level. And the second tricky question is, are assets single or multiple product friendly? And the third area, reconfiguring supply chains for resilience. It's a topic that's absolutely taken over my world over the last 2 years. I'm actually at Davos next week, and every panel has slipped in the word resilience into the topic. So can our manufacturing technologies give us confidence that our product is going to get to market? So what I wanted to do was just have a look at how modular microfactory supply network architectures might provide a solution to this problem. And some of the new work in this space is how do we minimize the transaction costs through algorithmic derivation, alternative supply options, and trying to look at how do we evaluate one option versus another. And the old problem in supply chains is what inventory and where do we keep it. Now I want to start the conversation around the broader CMAC workflow. And you see here molecule selection, product spec, going through particle design, process design, selecting the right workflows, and then finally identifying product process archetypes. So what does this mean to our supply chain team in Cambridge? And so we've got another layer here around, we might examine the first part of that in terms of patient populations and segmentation. And some work we've done on what the product archetypes might be that would be amenable to continuous processing starts to look at what types of volume and variety products would be amenable to this type of technology. The second area on product process archetypes is trying to look at what technologies are viable at those volumes and at that level of product SKU, stock keeping unit flexibility. And finally, once we've unraveled the product and the product process limitations, what's the viable supply network design? And I wanted to just very quickly talk through our work in Cambridge in this space. So the first and foremost was around product selection. And often we were asked, I was very surprised when CMAC colleagues were asking me what molecules should we be working on. Yes, and so it's a viable, it's a valid question, and we started to look at, essential medicines, what's being used in the NHS, for example, in the prescription data, how might this inform API selection? And do we look at this at therapeutic area level, or do we look at the API level? And this is now a structured process for trying to identify targets. And we identified a number of APIs and a number of therapeutic areas. Going through that process, this is an example of that process, going through various data sets to identify potential targets in terms of API, whether they were classified as essential medicines within the NHS prescript data set, was it in shortage, is it a single sourcing route, what product format are we concerned about, and is indeed there's a UK manufacturing base. And over the last year, of course, we've been having a look at, is there a COVID interest within this? And one of the things you sort of identify here, yes, you can identify products that might be influenced by whether they're in short supply. You may also be influenced by what the current sourcing arrangements are. And you see on the right-hand side, a lot of the medicines are imported, and the so-called UK manufacturing base is largely an importing process rather than a manufacturing process. And you'll have noticed that many of these, in fact, there was a news story just this week, another 4, I think, importing organizations were going into administration. It's not a really viable activity at the moment for certain products. So that's a little bit about what products should we be working on. Then around process technology selection, and here we developed some of the metrics that you might look at selecting an API, or some of the factors that you might look at selecting an API or a product. And we've extended that to look at some of the supply chain factors. And this is one of the very interesting things around API selection, starting off with molecule selection. Invariably, the way we would look at a supply chain problem is looking at where the demand is and what's the product flexibility required on the demand side. So we're integrating a number of factors here. So looking at both reaction technology and also incorporating the supply chain. And starting to look at market needs, addressing shortages and essential medicines. Through our AHP analytical hierarchy process, started to look at the influence these different factors might have on selection by reactor type. And then we've now revisited that product process, that product selection chart that I showed earlier into that product process archetypes. So starting to understand some of the limitations of certain reactors and trying to overlay that with product selection. So that's a paper that's just been published this last year. Now, the third dimension to that was around evaluating the business case for continuous microfactories. And this we've pulled together all of our thinking in this space, and that's in that book chapter on continuous pharmaceutical processing. And I'm not going to repeat some of that output here because that's available. I'm going to just touch on where we're thinking of taking that work forward. And if you make your way to poster 24 during the breakout sessions, some of the things we'll be looking at is how do we extend from that analysis into the type of supply chain and manufacturing footprint architectures we might consider. So would we focus on single products or multiple products? And are those facilities centralized or distributed? And some of that work is set out in poster 24. So here we're starting to look at the business case by bringing in this whole area of location, production flexibility, multiple products, capital investment, and utilization. Some of the fundamentals that would go into any analysis of whether an investment is justified. I want to now close off with some work we've been doing around modular microfactories in particular, And does the approach offer enhanced supply resilience? Now, we did some work with NHS sourcing in the UK and various other organisations, devolved organisations, both in England, Scotland, in fact, in Northern Ireland as well, and started to understand what is the procurement strategy for products. And I was somewhat surprised that the procurement is pretty much of the finished product. There isn't a consideration of NHS and its sourcing unit investing in APIs. Could that involve a selective API sourcing and advanced manufacturer strategy? Is there investments in finished product? It requires the ability to process APIs through own or secure production and on an ongoing basis through perhaps contract manufacturers. And finally, is there investments in late customization, late pack customization? And you'll have noticed in that earlier chart, dose format was a major reason for product shortages. So even late finishing could have a major impact on security of supply. And the other key dimension to this is, can we look at flexible pack formats and prioritization also based on therapeutic need? So therapeutic need is indeed also a variable to consider. So at the moment, the supply strategy is a single point at the distribution usage interface, and without much consideration of the opportunities upstream in API, formulate, and packaging. Now, we've been looking at some network theory papers in this space, and trying to look at, within those green boxes, you're really having knowledge-intensive task dependencies. And between those, you have those thin crossings. They're mundane transaction costs. There's where there's opportunities to actually make an intervention. So here, we've been starting to look at how does this play out in terms of modular microfactories as alternative supply chain solutions. So, as I mentioned, it involves material and knowledge interdependencies, but also provides the ability to retain stake in the game. If the current sourcing strategy is of the finished product alone, then knowledge within that supply chain is very limited. Indeed, our thin crossings, as I mentioned, rather thicker than they seem because the current procurement practice that's deployed. And should their locus be re-examined, does continuous processing and modular microfactories actually change where that knowledge intensity is and where it sits? And just to explain a little bit on the right-hand side, apologies, is the intervention options on the right-hand side, whether it's around dual sourcing, whether it's around national stockpiles, or whether it's about repurposing across different therapy areas, or indeed the many projects we get involved in, which is different supply routes direct to patient. Now, my team has been looking at a number of products to exemplify this activity. Quite a few of their products were banned substances, and I was getting a little bit worried, so we went for some broader products and started to look at what were the thin crossings across the different stages. And you start to get a sense of the knowledge you need to operate in certain parts of that extended supply chain, and where the opportunities were to have a transaction cost approach. Now, so this was dexamethasone as an example, and we started to just test the concept, whether we can determine this algorithmically. So we took a COPD product, looked at the bill of materials, started to see, can we identify algorithmically where those thin crossing points might be. It's quite fascinating. We shared this with BEIS, with UK government, and they're very much also looking at a very similar process. Indeed, they're actually looking at thick crossings. Why are there supply security issues in a number of our supply chains? So this is quite a fascinating piece of work, trying to look at different interfaces. Where should the interventions be? Where are the transaction possibilities? And does it give us greater flexibility in supply security? And some of the theories that we'll be using to determine that. So this has been tested in the COPD example, and hopefully will give us some more insights on how to manage that extended supply chain. So just to wrap up, going back to the earlier charts, the design of microfactory supply chains, we've looked at molecule selection, process technology constraints, and how they impact supply network analysis. We've looked at how multi-criteria decision-making techniques and structural modeling can be used to really ascertain expert-driven technology selection and decision-making. And some of the new work we'll be looking at integrating both quantitative inputs as well as qualitative expert input. And then looking at that supply network design right the way through that digital twin supply chain and indeed the digital platform context, which I haven't really had time to get into at the moment. I've talked about modular production network options for supply resilience, so that's around that algorithmic derivation, looking at the value of different options in terms of modular architectures, and also then looking at the implications for safety stocks to provide greater resilience. And finally, just where we're heading next is can we use these techniques to look at more CMAC-specific exemplars to explore alternative supply scenarios. Particularly what we'll be looking at is cost and service levels. Now, there's some great linkages of this modular microfactory with a number of new projects. DM Squared, I think many of you will have heard of, and there'll be more to hear. Tomorrow, of course, we're also part of two other Innovate UK projects looking at the digital information flows within an extended supply chain. And does this give us an opportunity to be more adaptive? A number of references of our publications that have come out over the last few years. The latest very much looking at some of the work I've just presented. A shout out to Etere and Paminda for their work in this space. Poster number 24 is where you can get some more detail. And just to also introduce CMAC Kabari. You might think we're naming our researchers with CMAC, but it's not quite the same. So CMAC will be joining the team and will also be giving us great input on some of the multi-criteria decision-making. So thank you very much, and I'm open to questions.